So this is an application of what we have been discussing in the elevator case. This is in a plane, in the atmosphere. They are not in space. Yes, this is a plane, just a plane. This is where they train the astronauts. And this is basically how it works. So you have this, then it accelerates, then it starts to rise up. After it has risen sufficiently fast, remember a free-falling object, that is an object that is just moving freely only with the influence of the gravity, will have an acceleration given by the gravitational acceleration. So if our elevator was falling down with the gravitational acceleration, in that case the weight will be 0. So if this AE was equal to this gravitational acceleration, minus g, then your weight will be 0, you will start flying. So this is what they do. So you have this plane, it starts to rise up. After some point, well, we know what an object with constant acceleration does, how it moves. It makes a parabola. So this is a parabola. It goes over, it flies through a parabola, the plane. So in that parabola, the acceleration of the plane is exactly g. So it cancels the weight of the astronauts. So the astronauts are just weightless. Now, of course, then here, at this, it starts going down. At some point, it has to accelerate upwards. But if it accelerates upwards, here the astronauts start feeling larger than the g. So it's almost their usual weight. So if they want to use this thing, they enjoy this 0 weight limit, they also have to suffer the huge weight limit. Now let's look at some other examples of applications of Newton's law. In most of the applications, when you apply a force on another object, okay, you can just go there and pull it or push it, or you can just attach a string, and with the string you can just pull the object towards you. Now if you consider a string, a piece of a string, let's say this is a string of some length, you apply a force F on one end of it, the force F prime on the other end of it. So again, Newton's law just tells me that the total force acting on my object, which is nothing but F prime plus F prime, this should be equal to the mass of the string, the total mass, times the acceleration of the string. Now, if the mass of the string is a very lightweight string, if the mass is almost 0, then the net force acting on the string should also be 0, independent of the acceleration of the string. So whether the string is accelerating or not, the net force acting on it should always be 0. It just tells me that along the string, the forces at both ends of a given string, let's say, are just opposite in direction, but equal in magnitude. So if two vectors add up to 0, it just tells me that they have the same magnitude, they are just pointing in opposite directions. So this is what it tells me. Now the magnitude of force is what we call tension. So if you consider half of this string, if you divide the string into half from here, in that case, this part of the string will be pulling this part of the string, and the force that this part of the string exerts on the right part exerts on the left part will also be equal to have the magnitude given by this tension T. So the tension T is just a number. It's not a vector, it's a number. It is the magnitude of a force. It's a number, and it is the same number along the string, assuming the string is massless. If the string has a mass, then the tension will change according to where you are, whether the string is accelerating or not. But in this limit, if we neglect that the string is neglect the mass of the string, then the tension along the string will be constant. So this is something we will use in the examples. Well, the simple example you can think of. You can say that, okay, this is mass M2 is you holding a rope which is attached to some other M1, and you are pulling your friend. You are pulling the mass M1. Now we can draw the free body diagrams. These are the free body diagrams for both of the masses. Each of the masses is pointing downward, omega 2 is pointing downward. Each of them feel a normal force, that the ground exerts a normal force on my masses. This mass is pulled by the rope, let's say by a force given by F1. Now if you look at the other mass, there is this external force F. If you remember the original figure, the two masses are attached and M2 is being pulled by the force F. So there is this external force. This is the force due to the tension of the string acting on my mass. Let's call it F2. So these are all the forces acting on each one of my masses. I have two masses. I just ignore everything else. I just draw the masses and all the forces acting on them. This is my free body diagrams. There is no motion in the vertical direction. They are all lying on the ground. We are assuming that you are not pulling them up. So it just means that in the vertical direction, only omega 1, n1, omega 2, n2, they have some components in the vertical direction. So omega 1 plus n1 is the net force in the vertical direction. Since the acceleration in the vertical direction is 0, this should be 0. Omega 2 n2 plus n2, this is the net vertical force acting on my mass m2. It should be 0. The string is massless. So just using the previous result, okay, if the string exerts the force F1 on this mass, then this mass will be exerting a force on the string. They are action-reaction pairs, and the reaction force will be minus F1. F2 is the force exerted by the string on my mass, but then my mass will be exerting a force on the string, which is given by minus F2. So these are the two forces at two ends of my string. But the net force acting on the string has to be 0. So this just tells me that this force F2 over here should have the same magnitude and opposite direction to this force F1 over there. Let's look at how many unknowns we have. So we don't know the acceleration. That is one unknown. I don't know F1, I don't know F2. So I have 3 unknowns in my equation. This is one equation. I need 2 more equations. Well, I can use the Newton's second law, F equal to ma basically, to obtain 2 more equations for each one of these free body diagrams. Well, the net horizontal force on this first mass is just F1. This should be, this is also the net force acting on the first mass because these two cancel each other. So F1 should be equal to m1 times A being the acceleration of this one. Here is the plus direction here is F2. Components of F2, for example, if you x-axis, x component of F2 will be negative. In terms of the components, F1 is equal to M1A, F plus the horizontal component of F2, which is minus the horizontal component of F1. F1 can be both positive or negative. I'm just adding all of the vectors. The direction here is determined by the component sign of the components of these vectors. It is like, instead of writing 3 minus 5, I'm writing 3 plus minus 5. So that's exactly why I have this plus sign. I'm always adding, to obtain the net force acting on an object, you always add, sum them up, the force vectors. The directions are all taken into account by the components of those vectors. Well, this just gives me if I just only consider the, well, here I made an assumption. I use one more fact. I use the fact that I am assuming my string is not expanding or shrinking. So it basically means that if my first mass or if my second mass moves by 5 meters, this mass attached to it by the string also moves 5 meters. Their displacements are exactly equal at all times. But if their displacements are exactly equal at all times, it just means that their velocities are equal at all times, because velocity is nothing but displacement at a given time. So these displacements are equal means velocities are equal. If the velocities are equal at all times, then their accelerations have to be equal, because acceleration is nothing but the rate of change of velocities. So if velocities are always changing at equal amounts, then acceleration should be the same. So these two accelerations, the accelerations of these two masses are the same. Well, from here to this equation, what I did was, okay, I just wrote F1. I didn't write it explicitly, but F1 vector, the horizontal component of F1 vector is F1, and the horizontal component of the F2 vector is F2. So F1 is nothing but m1 times a is the horizontal component of the acceleration. F plus F2. F2 is the horizontal component of the force act of this vector force. You see here it's F minus F1. It has the same magnitude as this one, if F1 is positive, let's say. So the net force acting on this one is F minus F1. So the minus sign automatically came. I don't need to insert the minus sign. Yes?
And why don't we have a vector?
Well, because here, okay, I should have probably added it. Here I'm talking about the vectors. But in this problem, since omega 1 and n1, they all cancel, all the remaining vectors are along the horizontal direction. So which I can call the x-hat direction, let's say. So here, these equations are for the components of all these vectors along the x-hat direction. So you can just, if you want to write this everything in terms of the vectors, this equation is just f1 along the x-hat direction is equal to m1a along the x-hat direction. I just cancel the x-hat directions. Well, the rest is just algebra. If you just sum them up, f and f1, if you sum this equation with this equation, f1s, they just drop, so f is equal to m1 plus m2a, or the acceleration of the whole system is f divided by the total mass of the system. Well, this is in fact something we had expected. Since the first example we have been doing, we were talking about large objects, and we were saying that the acceleration of a large object is given by the net force acting on it divided by the total mass. We didn't specify how the various pieces of this large object was connected together. So if you just imagine this system as our large object, the total mass of this large object is m1 plus m2. The net force acting on my large object is F. So the acceleration is the net force, the total force, divided by m1 plus m2. So the result is not something of a surprise. Well, we can also calculate this tension over there. Once we have the acceleration, well, we know the acceleration. Just multiply it by m1, and it gives you the f1. So it turns out that f1 is a positive number. So f1 is, well, this was our positive x direction. f1 is positive. It's in this direction. But F2, since F2 is minus F1, F2 is pointing in the minus x direction. So the sign automatically comes from the derivation, yes.
If I am pushing something, but I'm pushing it,
Okay.
so our accelerations are not the same.
If you are constantly in touch with the object, then your accelerations are same. They are the same. Because they are always at the same position. If they are always at the same position, that means their velocities are the same at all times. If their velocities are the same at all times, their acceleration is the same at all times. Now I will, okay, any questions from this example, any other one? Well, I will come back to this example later on. There was a question. So the question was, if you are in a car, the car is accelerating, what pushes us backwards? So let's just imagine that this frame is our car. On the car, there is a fixed point. And on that fixed point, you attach a ball. Now, I don't know if you remember the times when in the minibuses, in dolmuşus, you had all these CDs hanging on the mirror. Well, you can just say, okay, this is the CD, and this is the mirror. The CD is attached to the mirror. And you probably remember that as the dolmuş accelerates or decelerates, the CDs are just moving around wildly. So if you see such a thing, when you see that the CD was just straight down, then you can tell that the dolmuş is either at the bus stop or it is moving at a constant velocity. Well, I mean, you know that the dolmuş should never move at constant velocity, so the dolmuş is on the bus. On the bus, the dolmuş stop. But when you see this one, you know that the dolmuş is accelerating. Well, you always see something like this. It is either accelerating in one direction or the other direction. So I'm assuming that this is a time-dependent force. So there is an acceleration in this direction. If there is an acceleration in this direction, then we know that the ball will swing backwards. And in fact, that is what we would think, that there is a force pushing us backwards. Now let's study this in an inertial reference frame. So the magnitude of A I will denote by A. Well, as with all of these problems, first draw the free body diagram. This is my free body diagram. The Y is the vertical. The X is the horizontal. My acceleration, I'm assuming that it is in the positive X direction. And well, there are two forces acting on it, the weight and the tension. Those are the only forces acting on my object. The acceleration vector is given by this. Well, in these coordinates, I can write my force vectors. The weight is minus mg along the negative y direction. The tension, well, it has a component along the y direction, which is nothing but t times cosine alpha, the tension force. And then it has a component along the x direction. It is just t times sine alpha. T times sine alpha along the x direction. Well, the total force acting on the CD is just the sum of these two forces. So along the y direction, I have t cosine alpha in the positive y direction and minus mg in the negative y direction. And then I have t sine alpha in the x direction. This is the total force acting on my object. Now we know the Newton's second law. It just tells us that the total force acting on my object is nothing but mass times the acceleration. Well, the acceleration is the acceleration of the suspension point. So as the mirror of the dolmuş is accelerating, it will be oscillating back and forth. But in the rare event that the acceleration of the dolmuş is constant, after some point it will also be stationary. Well, we will just assume that this wobbly behavior at the beginning has just faded away. It died away. So everything is steady now. I have a steady acceleration. The CD is at its position fixed. It's not moving around. So in that case, the acceleration of the CD will be the same as the acceleration of the suspension point. So both of them will move with the same velocity and hence the same acceleration. So the total force has to be mass. The total force acting on the CD has to be the mass times the acceleration of the CD, or the acceleration of the suspension point. Well, this is one expression of the force. This is what that force should be from Newton's second law. So it just tells me that along the y-hat direction, I see that the acceleration, the force has this component, t cosine alpha minus mg. But the net force, according to Newton's second law, shouldn't have any y component. So the t cosine alpha minus mg should be 0. Then from here, we know what the tension is, tension in the string is. Then if you look at the x component is t times sine alpha from this expression. But from Newton's second law, the x component of the force has to be mass times the acceleration of the dolmuş. So if you just substitute this expression for tension here, you get sine alpha divided by cosine alpha, which gives you tangent alpha. So mass times the gravitational acceleration times tangent alpha is mass times a. Or tangent alpha is just acceleration divided by the gravitational force g. So if inside your dolmuş you can measure this alpha, just use an angle measuring device. You can measure this angle, and using this angle, you can determine what the acceleration of the car, of the dolmuş is relative to the acceleration of gravity. So in this problem, there is no force that pushes this backwards. Or in your case, if you are sitting in the car, if the car accelerates forward, you feel that there is a force on your back, right? So you feel as if there is something pushing you back. But what is actually happening is the back of the seat is pushing you forward. So that's why you are feeling a force on your back. You are exerting the reaction force. You are exerting a force backwards on the seat. The force that you are saying is backwards is the force that you exert on the seat, and not the force that the seat exerts on you. We have one more example, but before that, let's have some votes. So this is your question. So there are two people. Okay, let me start the voting. Okay. Probably a very few of you watched the video that I suggested you to watch in the first lecture about this lecturing thing. There the speaker tells one of his experiences. He does the exam that you had done in the first day. And after some point, one of the students asked, should we answer these questions according to the way you taught us? Well, he did it not in the first day, but in several weeks. Should we answer this according to the way you have taught us, or according to the way that we usually think about these things? If you are thinking other than the way we have taught us, you are thinking in a wrong way. Physics, the thing we are doing is the real thing. Well, we already have 37 votes. Well, after this point, there will probably be peer pressure, and nobody will say vote anything other than the C. I think you have the right answer here. Well, there's a similar problem. Well, you know that they both feel the same force. Now, the difference is that which one will have a larger final speed? Vote. So it is the same situation. You have the daughter and the small daughter. You have the father and the small daughter, which is lighter. So they push each other. In the previous problem, you were asked which one felt the larger force. In this problem, you are asked to tell which one will have a larger speed at the end. In the previous problem, they were just action-reaction pairs, the forces, so the magnitudes had to be equal. So apparently these things seem to be quite clear. I will repeat the same question in several weeks and see if you still remember these things. Well, in the previous one, we agreed that they feel the same force, the same magnitude. The force they feel will have the same magnitude. Well, if they have the same magnitude, the lighter one will have a larger acceleration. Well, the force applies for the same duration of time, because once the contact is broken, there will be no force acting on any one of them. So the daughter has a larger acceleration due to her smaller mass at the same time as the father. Since the acceleration is larger, the final velocity will be larger. So the daughter will have a larger velocity. You are in a car, and the car takes a left turn with constant speed. So what is the direction of the force acting on you? Oh, sorry. Well, you are curious about the question. I'm curious about the results, the votes. Okay, so in this case, you might be able to find somebody who thinks different than you sitting next to you. So did you ask your neighbor what they think? What they answered? Well, that's what I call the peer pressure. But you have seen one case in the last lecture where the peer pressure led you to give the wrong answer about the helium balloon. Well, okay, most of you also got this right. Well, for those 20 people, what is going on is initially your car is moving in this direction. So you have your velocity in this direction. As you take a left turn, your velocity is pointing in this direction. So initially this was your velocity, finally this was your velocity. So the change in your velocity is from this one, this vector to this vector. So this is the change in your velocity. Since your velocity has changed, well, this is almost towards the left, let's say. Since your velocity has changed towards the left, the acceleration that you felt is towards the left. So Newton's second law just tells me that the force you felt is towards the left. And if you think over it, that is actually what you feel in the car. The car pushes you towards the left. You are pushed, there is your reaction force. Since the car pushes you towards the left, you are pushing the car towards the right. The force that is towards the right is not the force acting on you. It is the force acting on the car by you. That's your reaction force to the push of the car. So, any questions on the previous 3 questions, by the way? On these voting questions, any questions left? Most of you got the answers right anyway. So our last example. Well, if you go to any commercial centers, commercial shopping centers where they have these shiny elevators made of glass, you will see that as you move up and down the elevator, there is a huge block of metal that moves in the opposite direction. When you move up, the mass goes down. When you move down, the mass goes up. So it is basically this machine over here. There is a pulley over here, and the 2 masses. One is the elevator, the other one is so-called the counterweight. So the counterweight is put such that the motor that is supposed to rotate this pulley doesn't need to create a huge amount of force. With very small amount of force, it can lift you up and down. It balances the weight of the elevator. Now, the question is, in this simple example, we don't have any motor. So we will assume that it is a massless pulley, because if it has mass, then we have to apply a net force on the pulley to start it rotating. But it means that the tension at this side of the rope will be different than the tension at this side of the rope. We will study this rotation motion in future weeks. But for the time being, assume this is massless. So in that case, well, the string is also, we will assume it is massless. So the tension along the string is always constant, which means that if you cut the string at this point, or if you imagine that this point, the upper part of the string is pulling this mass towards the upwards with a force whose magnitude is equal to the tension of the string. As usual, we choose the coordinate axis. These are the forces acting on my masses, their weight and the tension. Just to get rid of all the clutter, we have already used the fact that there is a pulley, there is a string in determining these forces. And these are the only forces acting on my masses. So these are my free body diagrams for these masses. And, well, let's see. The accelerations of each one of these, I can just call them A1 and A2. Their Z, everything is along the Z direction, either up or down. So all the X and Y components of the vectors will be 0. So A1 vector, I can just write it as A1 along the Z-hat direction. This is the Z component. This is not the magnitude of A1. This is the Z component of A1. If A1 is positive, then I know that my mass A1 is moving, accelerating in the positive z direction. If A1 is negative, it is accelerating in the negative z direction. The A2 vector has the z component A2. T1 force has the z component T, which is the tension of the string. Well, this should be T2. And the T2 force, this force acting on the second mass, it is caused by the same tension. So the tension here is also the same as this one. Tension along the z direction. Now, these accelerations and the T are the things that we do not know. We would like to find the acceleration. Well, we don't really care about the tension at this step. Well, it will be important to choose this string. Your string should be strong enough to support such an acceleration, such a tension. Okay, the AIs are unknown. The weights, they are in the minus z direction, both of them. The weight of one is minus m1g along the z direction. Weight of two is m2 times g along the minus z direction. Thank you. Thank you. So I suppose that woke you all up. Well, I will just, from this point on, I will use the Newton's second law. F equal to ma. So this is the net force acting on my mass m1. It should be equal, well, rather than writing a different equation for the mass 1 and mass 2 separately, I will use such a shorthand notation. This just means that for I equal to 1, you have such an equation, and for I equal to 2, you also have the same equation. Then I know that the time forces, T1 and T2, they have the same z component. So here I have a vectorial equation. Here I write the z component of the same vectorial equation. So Ti, the z component of T1 and T2, they are both T. The z component of the weights is just the corresponding mass, gravitational acceleration. So it is T with a minus sign. T minus the corresponding mass times T is equal to the corresponding mass times the acceleration. So I have two equations here from Newton's second law. But remember, I have three unknowns, two accelerations and the tension. So I need to find one more equation, which doesn't follow from Newton's second law. But then I will use the one fact. I know that if this mass moves up by 1 unit, the other mass moves down by 1 unit. So that is the displacement of this mass and the displacement of this mass, they have equal magnitudes, but if one moves up, the other one moves down. They have opposite directions. But if the displacements are equal but in opposite directions, it just means that their velocities have equal magnitudes, but they are moving in opposite directions. So the velocity of the first mass is equal to minus the velocity of the second mass. This should be valid at all times. Otherwise, if this is not satisfied, either the string will break up at some point, or the string will get loose. So for example, if this mass is stationary, the other one is moving up, then it breaks, the string becomes loose. In the other extreme, if you just pull this mass down, then the string should break if it forces to move down. So the velocities have to be related by this. And which means that the accelerations are also related. So this is what I know. This just means that this A1, the z component of the A1, the acceleration of the first mass, is minus the z component of the acceleration of the second mass. So I have three unknowns and three equations. Two from Newton's second law, the third from the fact that these two masses are attached by a string of constant length. Now these are our equations. Well, you can just subtract this one from this one, use the first equation. It just gives you m1 minus m2g is equal to minus m2 plus m1 a1. You obtain a1. This is just simple algebra. Okay, we have an answer. Now we have to ask ourselves, does this result make sense? Is it what we would expect from our general knowledge of how things work around us. We can test certain limiting cases. One limiting case would be if the two masses are equal, then you know that the things are balanced, so there will be no acceleration. If they are at rest initially, they will stay at rest. They will not move at all. Well, if the masses are equal, m1 is equal to m2, then the acceleration goes to 0. Well, that is a limit which follows our intuition about how things work. We can consider another limit. Let's just assume that m2 is very, very heavy. You can just imagine that you are m2, and there is a snake trying to, well, you are this m2, you are falling down a cliff, and there is a snake trying to hold you. So will the snake be able to balance you? There's a fly, let's say, not a snake, a fly. It's trying to balance you. Will it be able to save you? Well, let's see, if m2 is very, very large compared to m1, we expect that the acceleration of the first mass to be upwards. So a1 should be positive. Large. M2 is very large. Then A1, well, we can ignore M1 compared to M2. Let's say this is 1,000, this is 1 kilogram. Well, this is minus 999 divided by 1,001. This is almost minus 1. So if M2 is very large, you can just ignore M1. So you have, ignoring M1, this ratio is minus 1, we have a minus here, so A1 is almost equal to G. Well, that is what we expected. So the fly just moves upwards. So the fly will not be able to stop you from falling down the cliff. We can imagine the other case. There is a fly attached to the other end of the string. She is hanging on top of a cliff, and you are trying to hold it. You would expect that since M1 is very large, mass 2 should go up, mass 1 should go down, which means the acceleration of the first mass should be in the minus z direction. But the A1, this number A1 over here, is the component of the first mass, the acceleration of the first mass along the z direction. So if M1 accelerates downwards, it means that A1 should be negative. If M1 is very large, you can neglect M2. If you neglect M2, M1 divided by M1 gives you 1. So the A1 is just minus G. That is, the first mass is accelerating downwards. Well, that's again what you expected. So we have the general solution. We can compare this general solution with our intuition in 3 different cases. And in both cases, they both agree. So it's probably that our intuition and our results are valid. But if what we expect does not match what we find in the equations, there are two possibilities. Either you have made some mistake in the calculation. It's quite likely that one misses a sign there or a factor of 2 over there on the other place. Or your intuition is wrong. If your intuition is wrong, that means that there's something that you don't really understand about the physics going on in that problem. So that will be a hint for you that you should think more deeply on these things. So you should always, always compare your intuition with what you obtain, with your results. Ideally, they should always match. If they don't, that is an opportunity for you to learn something new. Any questions? You can discuss it in the recitations. I will give your assistants the questions and you can discuss it.
After this year, will we get another exam like that?
They are supposed to be surprise exams to measure how much your way of thinking have changed rather than how much you have studied the day before the exam.